recognizing what intermolecular forces exist between molecules is the important part now. So the best thing we can do is, what we want to do is we want to know, well, are these going to be dipole-dipole attractions, hydrogen bonds, or London dispersion forces? And the first thing we need to do is we need to draw some molecular structures. So let's just say you were given the example of HBr, and you were asked what type of intermolecular forces are present. And so the first thing you would do is you would draw a Lewis structure. And so you would look at the number of valence electrons, and you would count the number of valence electrons, and you would add all your valence electrons, and you would end up with a skeletal structure such as this. So it's going to be important to be able to draw Lewis structures. And then you would realize that hydrogen is bonded to bromine, and because they're dissimilar atoms, there's most likely going to be a polar bond. And you could look up the electronegativities, but the vast majority of the examples that we talk about in this class, if they're dissimilar, they're going to be a polar bond, except for carbon and hydrogen. And so here, in this case, we would know that you would have a positive end and a negative end. And so we could ask the question, well, first, is there a dipole? Is there a dipole? And the answer is yes. Do you have a polar molecule? And if you answer the question here, remember, in order for a molecule to be polar, one, it has to have polar bonds, and two, it has to have a separation of charge, such as the molecule is polar. And so this is yes. So is it a polar molecule? Yes. And then the next question we would ask, because this is yes, we would ask, is hydrogen directly bonded to NOF? And the reason we ask this is because there's a special case of dipole attractions called hydrogen bonds, where hydrogen is directly bonded to NOF. And so in this case, the answer to this is no. And because it's a polar bond, we can say this has dipole, because it has a dipole, attractions. And so in this particular case, dipole-dipole attractions are the intermolecular forces in HBr. And so we could look at another example. If we were told, we were given CH3Cl, which is what's called chloromethane, and you would draw a Lewis diagram for this, and you would draw a Lewis structure for this. And at this point, you would say, well, I need to realize that this is a three-dimensional molecule, and so you would draw a three-dimensional picture of this so that you knew what the shape of this molecule was. And this comes from Vesper theory. And the first thing you would want to do at this point is to say, well, is there going to be a polar bond? And there is going to be a polar bond here between carbon and hydrogen. And just to note, carbon to hydrogen is non-polar. And I think I just said carbon to chlorine is non-polar. Carbon to chlorine is polar. This is a polar bond between carbon and chlorine. How do you know this? Because they're far apart on the periodic table. They're dissimilar atoms. And because of that, we want to say, well, is this molecule polar? This is the first question we want to ask. Do we have a polar molecule? And the answer is yes, because we have a polar bond, carbon-chlorine, and because we have a polar bond, the separation of charge exists. So this is negative, this is positive, this end is positive, this end is positive. And so we have a polar molecule. Because we have a polar molecule, we have dipole attractions, because we've produced a dipole. And why is it called a dipole? Well, it's because it comes from polar. It's a polar molecule or polar bond, and there are two of them because you have a plus end and you have a negative end. Just like you do on a magnet, you have two poles, the north and the south. In a polar molecule or a polar bond, you have a positive end and a negative end. And so if this is a dipole-dipole attraction, we could check that. Then we need to make sure that it's not one of those special cases. Is hydrogen directly bonded to NOF? The answer in this case is no. So this molecule has dipole-dipole attractions. And so this would be the intermolecular forces operating in this molecule. And so we could say, well, what about if you're given NH3, which is ammonia, the gas, you would draw a Lewis structure, and then you would say, oh, well, I need to draw a three-dimensional representation of this. And because from VSEPR theory, you have 4 domains around the nitrogen, so you would have 1, 2, 3, 4. This is a non-bonding pair. So this molecule at the moment is a trigonal pyramid, meaning that these hydrogens are pushed down by this electron, and this pair of electrons are pushing down on these bonds. And so the next question we're going to say is, well, what about polarity? Well, these are dissimilar atoms, so there's going to be some polar bonds, and these polar bonds are going to push electrons towards the central nitrogen. So this nitrogen is going to be slightly negative, these hydrogens are going to be slightly positive. So we do indeed have a polar bond, and we do indeed have a polar molecule because there's a separation of charge. And so because of this, because we answered the first question, do we have a polar molecule? And the answer is yes. So this means that we have dipole-dipole attractions. And because of this, we then always ask the question, well, is hydrogen bonded to NOF? And in this case, hydrogen is indeed directly bonded to nitrogen. Hydrogen bonded directly to nitrogen. Because of that, this is a special case of hydrogen bonding. And so hydrogen bonding is a subset of dipole-dipole attractions. It adds an additional attractive force, which actually is a very strong intermolecular force. In fact, it's the strongest intermolecular force. So hydrogen bonding is the strongest intermolecular force. I mean, it's nowhere near as strong as an ionic bond or a covalent bond, no way, but it's the strongest intermolecular force. And so because we've answered all of these questions, is it a polar molecule? Yes. Is hydrogen bonded to NOF? This is a special case of hydrogen bonding. So for ammonia, hydrogen bonding is the dominant intermolecular force. So that's important to always ask, is it a polar molecule? And then if it is a polar molecule, is hydrogen directly bonded to NOF? And if it is, then it's a particular case of dipole-dipole attractions called hydrogen bonding. And so let's just take a molecule, carbon with 4 chlorines around the outside. If you draw the Lewis structure, correctly, of course, you would come up with 4 chlorines around the outside. You would, of course, add all of your electrons, and then you would realize that carbon is bonded to chlorine, which is going to make a polar bond because they're dissimilar. And so there's going to be these 4 polar bonds here. And so we have polar bonds, but do we have a polar molecule? And the way we know if we're going to have a polar molecule is we have to know if there's a separation of charge. And so to do that, you would draw a 3-dimensional picture of it to get a sense of, well, what kind of molecule is this? And from Vesper theory, if you have 4 atoms around, if you have 4 electron domains or areas where the electrons are, you'll form what's called a tetrahedral structure. And each one of those bonds is pulling electrons away from the central carbon. And because it's a symmetrical molecule, as a tetrahedron, it's pulling those electrons away all at similar rates or at similar strengths. And so even though we have polar bonds, we actually have, in this case, a non-polar molecule, because there's no separation of charge. There's no separation of charge. And in order to have a polar molecule, you need to have a separation of charge. And because of that, we have a non-polar molecule. Now, if we have a non-polar molecule, we cannot have dipole-dipole attractions because there's no dipole. There's no dipole. And so if that's the case, if there's no dipole, we can't have, if we go back to our 3 potentials, we can't have dipole-dipole attractions because we don't have a dipole, because it must be a polar molecule. A subset of that is the hydrogen bonding, and because we can't have dipoles, we can't have hydrogen bonds, so the only thing left are London dispersion forces. And remember that London dispersion forces operate in non-polar molecules. So in this case, we would have London dispersion forces. And so those are some examples of how you determine what intermolecular forces are. And we're going to do quite a lot of these examples as we go along.